Our topic for today's discussion is communication channels. Basically, it's a continuation of my discussion yesterday in the previous class, where we looked at the block diagram of a communication system. We identified four major things there. There's an information source. We discussed the characteristics of the information source. There is a transmitter, the communication channel, and the receiver. We looked at the functions of all of these things. Today I'd like to speak a little more on the communication channel. If you remember, I did mention something about communication channel as a medium, to be thought of as a medium, and a communication channel as also an abstraction to model all the effects that take place in a communication system, or most of the effects that take place in a communication system. So I'd like to talk about both these aspects a little more in detail today for some of the communication channels. Now let me first talk about the effects that they model. So when I draw a box saying a channel, a communication channel, we are also representing the various effects that happen to the signal, that take place on the signal, right? The various distortions, the various noise additions that happen anywhere along the communication system. In fact, it may not even happen in the channel. The effect may not actually happen in the channel itself, physical medium itself. It may happen in the transmitter. The effect may occur at the receiver, but we blame the channel for everything, right? And we put the effect in the channel, right? And therefore we represent all the bad things or good things that might be happening to the signal and put it in the box called channel, right? For example, noise addition. We've been talking about addition of noise. Actually, noise is a very important issue in communications because there are a lot of sources of noise in a communication system. The sources of noise exist both in components at the transmitter as well as components at the receiver. Of course, some noise also gets added along the way in the physical medium, right? But not all the noise is added in the transmission. A lot of it happens at the transmitter and the receiver, particularly at the receiver. The noise added to the receiver is particularly very, very important and significant. But still, we put the effect in the channel. So channel is everything that we can't put either at the transmitter or the receiver directly, right? So that's an abstraction. So please remember that. To start with, let me discuss the channel characteristics in terms of noise. So noise, or types of noise that we encountered in channels. So when I say noise in channels, again this is to imply that noise in communication systems really, right? Channel is just a way of representing those effects. There are two kinds of noise sources that we have in communication systems. I should really say noise in communication systems. More precisely, and there are two kinds of noise sources that we can have, and we can characterize them as being either internal noise sources. Internal means internal to the communication system. Somewhere in the communication system there is a noise source, and therefore it is internal to the system, right? It is not coming from outside the system, right? There is one kind of noise. It may be in transmitter or receiver or the physical path, right? The other are what we call external noise sources. The external noise sources are typically what we also can say man-made noise sources, right? Sources arising out of some activities of mankind. That is, something is happening in the neighborhood which creates some noise or interference for a communication signal, right? So that becomes an external noise source or a man-made noise source. All right? Now, let me first take these external ones, external sources. I must slightly modify my statement. Not all external sources need be man-made, right? There can be external noise sources which are natural, right? So actually speaking, I should have said that the external noise sources are also of two types, namely natural and man-made. Let's talk about the natural sources first. One of the biggest natural external noise source is, correct, somebody is saying lightning discharges. Right? When lightning discharge takes place, a large amount of electromagnetic radiation takes place, right? And what is lightning? It's a very narrow burst of large energy, right? It's a impulse kind of signal. If you look at it from a signal point of view, right, it's an impulse kind of a waveform, right? A very large amplitude waveform, and it's obviously electromagnetic in nature, right? And therefore, it will have, what kind of spectrum does an impulse, ideal impulse have? Constant. The Fourier transform of the impulse is a constant function. So its spectrum is very wide, right? And therefore, it has the potential to interfere over a very large frequency range. Is it clear? So lightning discharges are very important from this point of view, because have the potential to interfere over a large frequency range. Actually, the spectral characteristics of these discharges, this noise source, is not exactly a constant, because after all, although we are saying it is an impulse, actually it is a pulse of some finite duration, right? That the duration may be very small, but it's still finite. And what is the spectrum of a pulse of any duration? What is the nature of the spectrum? Same function. Sin x makes a function, right? So if it is, so for example, if this lightning discharge duration is of duration tau seconds, what will be the nature of the spectrum? So the pulse duration is tau seconds, right? The spectrum would have the nature of sin pi f tau upon pi f tau, right? Now this is always between plus minus 1. So as a function of frequency, now what is the characteristic? 1 by f, right? So that means, actually speaking, 1 by noise, the lightning discharge noise, right, which is also called, sometimes these are called atmospherics. This kind of noise is also called atmospheric noise, right? Or simply, for short, we call them spherics, right? So this atmospheric noise due to lightning discharges actually has a spectrum which decays with frequency. So it is really more important at low frequencies than at higher frequencies. Now lower and higher is in relation to the various bands that I was talking about yesterday, right? So if you are carrying out communication in, let's say, the medium frequency band or the HF band or the maybe the VHF band, this may be significant. But as you go higher and higher in frequency, right, the effect of this noise will be smaller and smaller, right? And it will be particularly very, very important at low frequencies, right? For example, if you are doing communication at VLF, sometimes you do communication at VLF for very strategic applications, right? Or at medium frequencies, this noise becomes one of the major sources of disturbance for us to worry about. Okay? Good. So that's about the spectral characteristics of atmospheric noise. In time domain, as I said, these are characterized, this kind of noise is characterized by, so that's the spectral characteristics. In time domain, this kind of noise is characterized by large amplitude would you like to complete the sentence? Large amplitude, narrow pulses, right? And therefore it's also sometimes called impulsive noise. So it is particularly important at low frequencies. Let's say in the this AM broadcast radio. Anyone knows what is the frequency band used for this application? Anyone can? Now, as communication engineers, you should know some of these things in your fingertips.
And of the order of 100 kilohertz?
It's slightly higher. It's of the order of 550 kilohertz to about 1.6 megahertz. Right? So it's particularly important for this frequency band because this is not a very high frequency band. Right? It's actually called medium frequency band, medium wave in the standard terminology. Whereas if you look at FM broadcast, would you know the range for this? It's greater than 50 megahertz. Right? Correct. You're saying you're right. Now this is much higher than 1 megahertz, right? And therefore it becomes relatively not so important, this kind of noise, because it doesn't have the potential to disturb us as much as it has in this particular frequency band. Right? Okay. Now, as coming next to man-made noise sources, there are many sources for this. I'll just mention a few of these here. You heard of corona effect in power? Many of you are from power area. So there is this high voltage power line, what is called corona discharges, and they have the same kind of behavior that the lightning discharges have, right? Just like any other discharge. Then if there are a lot of electrical equipment, let's say, which is operating in the neighborhood, which contains, let's say, motors or generators, electrical motors or electrical generators, you know that these motors and generators have a kind of switching going on all the time, isn't it? Where? Which part of the motor or the generator? The commutator, right? There's an on-off contact, on-off thing happening all the time, as there's a rotating part as the armature rotates, right? The contact between the armature and the outside world is through the brushes, and the brushes operate through the commutator. The brushes and this is constantly going through a process of on-off, right? As the armature rotates, right? And therefore that creates switching, and that again creates a kind of impulsive noise, right? So we call this commutator generated noise. Let's say in electrical motors. Similarly, in the automobile or the aircraft, if you are carrying out communication there are sources of noise there which are because of the machinery. Can you think of some? the aircraft or the automobile ignition noise. What are you doing? Ignition means what are you doing? You are creating a spark, right? Momentary spark. In every cycle of the engine cycle, there's a time during which a spark is generated, and that's of course a source of radiation and therefore a source of electromagnetic noise for us, right? So ignition noise in let's say automobiles and aircraft. Okay. Anything else you can think of? In the telephone exchange, what happens in the telephone exchange? Now switching takes place. You are connecting users as they dial the number. There are a lot of either mechanical switches. Of course, the age of mechanical switches is now over, but still there are electrical switches, right? You have to create a path between the person who wants to talk and to the person he has dialed, and the creation of that path has to do a lot of switchings, right? So again, at let's say electronic exchanges or at telephone exchanges, there is a lot of switching. So any place where there is a lot of electrical switching taking place, right, it's a source of radiation for us. Please remember that. And therefore a source of typically what we call impulsive noise. Right? You agree with this? And one attribute, one effect of impulsive noise is, okay, let's look at it a little differently for two kinds of situations. If you are, let's say, carrying out voice communication or analog communication, impulsive noise is at best an irritation, right? If you have heard of, if you try to listen to shortwave radio or AM radio, sometimes when this lightning takes place, you do hear a lot of disturbing kind of sounds, right? So it is an irritation, but you can still make out what is happening, what is being said, and perhaps the essence of the song that you are listening to is still intact. But when you are communicating data through the channel, this can be fatal to the data, right? Because during the occurrence of this impulse and for some time around it, the impulse, the amplitude of this signal is so much larger than the signal amplitude that it will overtake the receiver, right? And what you will finally get at the output may have absolutely no resemblance to the data that you actually transmitted, right? So it will totally kill the data that you actually transmitted. So impulsive noise is something that we must particularly worry about in digital communication, right? Not that it is not important for analog communication, but it is something very, very crucial to worry about in digital communication, because data would be entirely lost in the interval in which this large amplitude pulse interference takes place. It's obvious. I don't think I have to explain that too much. All right. Any questions? Now let me stay with the man-made noise sources, but in this case the man-made noise sources are not due to these other activities of mankind, but due to communication activities of mankind itself, right? So there is this so-called radio frequency interference that we must talk about, which is usually denoted by RFI, right? And this is due to the fact that you are not the only one who is communicating. Now this is particularly important when you are doing communication through free space using radio waves, right? You are not the only one who is communicating, right? There are lots of people who, particularly today, in today's scenario, in today's wireless communication scenario, this is a kind of interference which has become suddenly so important to worry about, which it never was earlier. Why? Because of the fact that there are so many mobile users, and every mobile user is operating at a certain frequency, right? Typically in a small neighborhood, they'll all operate at different frequencies, all use the same frequency in different time slots or whatever, right? But still, since there are such a large number of these users, there is bound to be interference, if not from within this cell, from just a neighboring cell or a couple of cells away, right? So radio frequency interference is today very important in view of the fact that there is very high density transmission environment today. Right? Particularly in the context of mobile communication in a big city, right? Due to mobile communication, but it can exist even otherwise, right? Because there are so many things, communication activities that are happening. There are the aircraft which are being guided to land at the airstrip. So there are a lot of transmissions taking place because of that. There is a broadcasting activity that is taking place. There is satellite communication that is taking place for various kinds, right? There is the radar systems which are operating in the neighborhood to track either your friendly or unfriendly aeroplanes, right? And so many communication activities are taking place all the time, and every communication activity is a source of interference to every other, right? Theoretically, unless they are highly removed from each other in the frequency domain, right? If they are close by, there is a potential for interference, and all this we call radio frequency interference. Now, although I have gone from natural external sources to man-made external sources, let me come back briefly to natural light sources in nature. And now these are natural sources which come from outside our terrestrial world, right? The natural radio frequency interferences. So I'm on the subject of RFI now. This radio frequency interference need not come only from other communication equipment on the globe. We can have radio frequency interference from outside the globe, right? For example, sun is the major source of everything to us, all kinds of energy. And amongst this all kinds of energy, there is a lot of electromagnetic energy in the form of radio waves, right? Most of the time when we talk about sun energy, we talk about the light energy and the ultraviolet and the infrared, right? But the infrared part, if you go low down, it's basically radio waves, right? So one has to keep that in mind. And of course, if you are doing optical free space communication, then it is directly a problem, right? So basically, stars like our sun and other stars, because even though the stars are very far away from us, each of them is a sun, each of them is a source of radiation. It looks as if it will be very small, but the collective effect of so many stars in the universe is not so small, particularly when you are working with very, very weak signals, right? All this noise, background noise, due to the extraterrestrial sources, again becomes significant, right? Of course, as I say, one man's food is another man's poison. What we consider noise is a very important signal for somebody else, right? Who? The radio astronomers, right? They are looking for those weak signals and trying to understand these objects, and we here are generating a lot of interference for them to observe, right? So it is exactly like this. For us, that's a source of noise. For them, what we do here is a source of interference in their work, because they can't observe these effects properly, right? And there is a lot of tussle between the radio astronomers and the communication engineers in getting the bands allocated, right? For example, we have have you heard of the giant radio telescope in India, in Pune and in Uti? And they work in a frequency band, and that frequency band is being endangered by the communication activities that are taking place now. So there's a lot of lesson that's going on in these issues. So radio frequency interference due to extraterrestrial sources. Right? For example, you heard of pulsars and quasars. Right? They are basically radio frequency information that astronomers are dependent on. They are sources of interference for us, or they are sources of information for them. Right? An interference source is an information source for somebody else. Right? Okay. We haven't done with external light sources yet. I think I'm coming back to internal now. We talked about this radio frequency interference from various places, internal and external. But let's think about a situation where your own communication activity can generate interference for you. Can that happen? Can you imagine the situation where the signals that you are transmitting can also be a source of problem for the receiver in a particular situation? Can you imagine any situation where
So like your microphone when the speaker, when the mic is right in place of the speaker, so there's a feedback in that.
right, feedback from where?
From the speaker to the microphone again and again and again, so that.
No, but where does the feedback come from?
So from an echo.
From an echo, right? From a reflection from somewhere, right? Basically what is happening is, okay, but the analogy is absolutely correct. So I'll give you full marks for that. So the issue is, you have a transmitter, you have a receiver. Ideally, there should be a single path of propagation between the transmitter and the receiver. Then there is no problem, right? So here is a transmitter. This is your transmitting antenna, okay? And this is your receiving antenna. Okay? If there is a single path of propagation between these two, no problem. But if, let's say, for various reasons, there are multiple paths that exist between the transmitter and the receiver, right? So the radio energy not only goes from one to the other directly, but maybe through some other indirect paths. Now the receiver is confused, right? It doesn't know which one is the right signal to look at, right? So, and what is more, depending on the relative delays of these paths, the signal here may be weak or strong. Suppose we take a sine wave and delay the different phases and add them you are adding the same frequency sine wave with different phases, right? Depending on the relative phases of these various sine waves of the same frequency, the net amplitude of the resulting sine wave may be either small or large. They may reinforce each other, or they may create destructive interference for each other, right? So you might get what is called, and if also it so happens that this multipath environment is not fixed with time, it keeps changing with time. It can happen that sometimes you get a constructive interference and sometimes you get a destructive interference, right? So signal is strong sometimes and signal is weak sometimes, right? This is what is called the fading effect due to multipath propagation, right? So signal fading takes place now because of this interference, and that's very, very irritating for in analog communication and very, very destructive to data in data communication, right? This is typically what will happen, let's say, in mobile communication, right? Because between the base station and your handset, there are multiple paths. It's not a single path. Why? Because the base station transmission is not pointed towards the handset. It's a general broadcast, right? When it's a general broadcast, you will get a direct signal from the base station to you, but also indirect signals which are reflected by buildings, by trees, and all kinds of sources, right? And if in addition you are also moving these various paths, they will keep changing with time. The actual paths do not remain fixed, and you will actually theoretically be able to see the effect of fading. However, the handset is so nicely designed that it does not allow the fading effect to come through to you, right? But that's a very good, very important signal processing challenge for communication engineers, to make sure that the fading effect does not finally reflect on the thing that you hear, or the data or SMS information or the internet information that you are transmitting to the mobile, right? So that's one of the great challenges, and a very important area of research even today. Okay, so for the internal and external, natural and man-made noise sources from outside the communication system, right? Remember, we said noise sources could be internal to the communication system or external to the communication system. Now let's return to noise sources internal to the communication system. The two most important internal noise sources. Remember the definition of internal noise sources? They are noises which are being generated within the components of the communication system, right? Where will they be generated? Anyone would like to make a comment? Where does noise get generated?
Transmitter and receiver.
No, precisely what is the mechanism? Would you like to say anything?
Maybe the contact point.
Medium is changing from the transmitter to the
No, I thought perhaps you have you read about electrical current. What is the nature of electrical current? Is it a very nice smooth flow of electrons that takes place, or is it something different?
randomization of slightly different.
Basically, electrons are always in a random motion, right? And when the current takes, so when there is no voltage applied and no current flows, this random motion still exists, right? When you apply a voltage and a current takes place in the conductor, current starts to flow in the conductor, what happens is this random motion drifts to one side, right? So there is always this random motion of electrons due to thermal energy that they contain, right? Depending on the temperature at which they are operating. The conductor is kept, right? So this is the first most important source of noise, which is therefore present in every electrical component of your system, right? Wherever there is a current flow, or even if there is no current flow, there is a thermal noise, right? So the first kind of noise, internal noise, is what we call thermal noise, right? There is a well-known formula for this, how much noise you will see, but we'll discuss those formulas later, right? It depends on the temperature at which the component is operating. So if you have a particular so you have resistors in your circuit, you have transistors, you have diodes, you have all kinds of electrical components, electronic components. Every one of these components generates thermal noise, and since you can have hundreds of thousands of these components in the system, the overall effect of this noise would be significant. It will not be insignificant, right? So this is one kind of internal noise. So this is due to random motion of free electrons. Of course, it is random motion of free electrons, not all electrons, right? In a conductor or semiconductor. The second kind of noise is called short noise. I do not know whether you read something about the, you have gone through some courses where you learnt about the transistors and the diodes, and perhaps in some context also of some vacuum tubes, in some context, maybe not. But in all these so-called active devices, we have charged carriers. Remember, you know that, right? You have the, for example, in a semiconductor, you work with electrons and holes, right? The charge carriers. Now, and typically they propagate from, let's say, one point to another point. Let's say go from the P junction to the N junction, P type of the material to the N type, and so it goes from one junction to another junction, right? And again, these charge carriers, and now we're not talking of only electron motion, right? We're talking of any kind of charge carrier that you might have. The arrival of each of any one of them, or these charge carriers at a particular point, will be totally random again, right? So that kind of randomness also generates short noise. So basically this is due to random, what we call random arrival of charge carriers. I'm not going to detail physics at this moment, but maybe we'll have time to discuss this separately later. Random arrival of charge carriers in various kinds of semiconductor devices. So you will have short noise in transistors and in diodes and things like that, right? There are slightly different kinds of physical effects, and that's why they have been given different names. And their mathematical models are also slightly different from each other, right? As to what these mathematical models are, we'll discuss them separately later. So much about noise. I think I've made a lot of noise about noise, and that's because noise is very important in communication systems, right? Now, the last thing I'd like to discuss in the context of communication channels is something about, let's say, propagation in a communication channel. That is, looking at the medium, looking at the communication channel from the point of view of how the electromagnetic wave actually propagates through it. So I'm looking at types of communication channels from this point of view. And again, remember my original point that I made some time ago, that we're talking about electrical communication, which happens because of transmission of electromagnetic energy, right? That electromagnetic energy may be carried in a pair of wires, through a cable, or through free space, or through fibers, right? So no matter which one of these two you look at, you can characterize all these communication channels from the point of view of propagation also, how the energy actually propagates in these various media. Okay? Now what do I mean by that? Primarily, you can talk about three types of channels from this point of view, right? And these are as follows. One we call simply the EM wave propagation channel. For want of a better name, but perhaps you could also call it a free space channel. The second one is guided EM wave. Propagation channel. And the third one, or really a subset of the second one, but it's still worth having a third kind called the optical channels. So now let's see, it appears as if we just are playing with words, but there is an important difference here between 1, 2 and 3, particularly between 1 and 2. Free space propagation cannot occur on globe, on the earth. Can you say why? Does this statement make sense to you? Because we are, there is no free space here. We are living on earth, right? So there is a free space. I mean, the atmosphere looks like free space to us, but it is adjunct, it is adjacent to the earth. So there is a boundary here, right? There is one kind of medium above the surface and another kind of medium below the surface. So truly speaking, anywhere on earth you can't have true free space propagation, but you can have free space propagation, let's say in space, far away from heavenly bodies, right, between 2 points. Because in free space propagation that you might have learned, the way basically the way propagates is through spherical wavefronts, right? Those spherical wavefronts are simply not possible to support in the neighborhood of any conductor, right, or in the neighborhood of any object which will disturb those wavefronts. And Earth is very much in proximity to every kind of situation that you will work with here, right? So free space channel really exists only in true free space, that is if you go in space, right? You agree with that? But let's look at approximately we can also have free space near in the neighborhood, provided make sure that you are more or less working above somewhere, right? Now I had this picture, but it was not coming very clearly, so I'll have to try it here now. Let's say this represents your Earth. This curve represents the surface of your Earth, and let's say you have a transmitting antenna somewhere here and some receiving antennas elsewhere. Okay? And what are various kinds of situations that are possible in terms of the way the propagation will occur between transmitter and receiver, right? One mode is the wave will propagate along the ground, right? For example, from a transmitter to a nearby receiver, the actual propagation follows, the propagation path actually follows the curvature of the Earth, right? You've done a course in electromagnetic waves, right? EM theory. So you know what happens when there is a medium which is bounded on one side by a conductor, right? What kind of wave gets supported? There's a guided wave. So this ground wave is a guided wave in that sense, because it is guided by the surface of the Earth, right? So this is called the ground wave. So this is a kind of guided. The conductor guides the wave along with it, right? Then you can have something like a free space propagation, or sometimes also called sky wave, if you are just transmitting up, transmitting away from the surface of the Earth, right? So for all practical purposes it will look like more or less a free space propagation, and which will be a typically line of sight propagation. For example, let's say when you are communicating from an Earth station to an aeroplane, right? So let me just draw the aeroplane like that here. A very bad drawing, but somewhere communicating with an object which is situated above this, considerably above the surface of the earth, right? Or a satellite, for example, you are making a transmission to a satellite. But then there is a slight difference between these two, which I will talk about. So suppose you want to communicate from here to here. See, ground wave is good, but ground waves will be supported in a fairly narrow frequency band, typically lower frequency band, the medium frequency band, right? As you go up higher in frequencies, what will happen? This earth looks like a conductor, but there is also, every conductor also has some problems. There is a skin effect and attenuation and things like that. That attenuation becomes so strong at high frequencies, and that the ground waves really cannot be used as a propagation mode for for communication over large distances, right? Because as you go up in frequencies, the attenuation increases significantly, right? So ground wave is really typically useful for lower frequencies or higher wavelengths. Now if you have lower frequencies, you can use ground wave quite nicely. When you go to higher frequencies, this is not very useful. However, this kind of thing is possible. Straight line propagation is possible like that, right? Straight line propagation is also possible. Let's say if you have two high towers on the surface of the earth and they can see each other, so line of sight is possible. The straight line propagation is possible at a higher frequency, right? So we call straight line or LOS propagation is possible. Now if you want to work at a higher frequency, there is then a limitation as to how much distance you can communicate, because the propagation will have to be a straight line propagation, a line of sight propagation, and because of the earth's curvature there is a certain distance beyond which you will not see, right? Depending on the height of the antenna here, maybe you can go up to here but not beyond, right? There is a tangent here, so probably you can only go up to here. After that the wave will be obstructed by the surface itself, right? So what do you do if you want to carry out high frequency communication between two largely removed stations, right? We need somebody to come in now into the picture which will reflect the wave back. So we will transmit the wave up and can be reflected back, and there are two ways in which it can be done. One is through a satellite, right? And the second one is through an effect that is present above the surface of the earth. There is a layer of charged particles somewhere about a couple of kilometers above, a few kilometers above the surface of the earth, which is called the ionosphere, right? So you have the ionosphere here, right? So this acts like a passive reflector for us. So if a wave is sent up, it will get bent like that. Of course, it's a very imperfect drawing. Typically, actual propagation path will look like this. Let me draw another picture. So between an antenna here and an antenna here, you may have a path here like that, and that reflection, of course, it's not a straight line propagation because there is a reflection taking place in the atmosphere itself, and this reflection is due to the presence of the ionosphere, right? So ionosphere is a very nice natural phenomenon which helps us to carry out long distance propagation at higher frequencies. But how much higher? Not for all high frequencies. It also has a limitation. The frequency must be less than about 30 megahertz or so, right? maybe a little this way or that way, but around this range. If your frequencies are still higher than this, then the way that you will transmit from here, you will skip the ionosphere. They will go out of the earth. They will never come back.
So this
They will not be.
problem can be there as long as the wave is in Earth's vicinity.
Sorry.
The attenuation problem for high frequencies will be there as long as the wave is in the Earth's vicinity, because there will be some problem over there.
Yeah, that's why you're sending it up.
So even when you're sending up, I should have the attenuation problem because the
No, attenuation is due to ground wave propagation. The ground wave, due to the high frequency, will attenuate very fast. But these will be due to the, of course, the standard propagation loss will always take place. Which is the standard propagation loss? The inverse square loss. Right? As you go away from the source, the intensity will be proportional to 1 by r square. Right? That will always be there. Of course, that is ideally true only in a free space propagation. This is not exactly free space, but roughly the same kind of thing will still take place. Maybe the power will vary. Instead of 1 by r square, it will become 1 by r to the power 3 by 2, right? Because this is not exactly free space. But other than that attenuation, the attenuation I was talking about along the ground wave was much more than this inverse square law, right? So at a higher frequency, at 30 megahertz or so, it will hardly propagate to a few meters along the ground. So you will not see it. So you have to use other means, right? So, but as I was saying, this mode of propagation is also useful only below 30 megahertz or so. If you are trying to communicate at a frequency which is much greater than 30 megahertz, right, the ionosphere doesn't help us at all, right? And the only way we can now do it is by having an active reflector or passive reflector much above the surface of the earth, so that the wave can go through to that and then be reflected back by it or retransmitted back by it. If it is reflected back, we call it a passive satellite. If it is retransmitted back, it becomes an active satellite. Okay. So I think this gives you an overview of the first two kinds of channels. Really mostly the first kind, and the second kind, the guided wave propagation, is partly the ground wave propagation that I talked about. But more importantly, amongst the guided wave propagation, you also have guided wave channels. You also have every kind of communication that takes place through cables or pairs of wires. Right? A cable, you normally look upon the cable or a pair of wires as if they are carrying current, and we talk about voltages and currents, but basically you are transmitting electromagnetic waves, right? Depending on whether you are working at a lower frequency or a higher frequency, you can treat them as lumped circuit representations, or otherwise you can't represent them. You have to work with them in terms of EM wave propagation. If they become transmission lines, right? We don't call them just circuits anymore. A pair of wires may look like a circuit, right? But if you do so only at lower frequencies of operation, where the size of the objects involved, the wires and the components, is much smaller than the wavelength. If your size of the transmission line becomes much larger than the wavelength, right, then no longer you can talk in terms of a lumped circuit model for them. You have to think of them as a means of propagating electromagnetic energy, right? Electromagnetic energy is being transferred, and the way you study these same things then is not through the same theory but through transmission line theory, right? So if you're working with cables or pairs of wires, or guided waves, waveguides for example, guided waves can also be in waveguides. You know about waveguides? Right? Waveguides are essentially either cylindrical or rectangular metal objects, pipes, through which electromagnetic energy is transmitted. For example, you could have an antenna upstairs, like we have here, and there is a transmitter electronic equipment sitting downstairs. How do we get the energy from there to here inside? We typically use a waveguide. Actually it's a pipe. Literally it is a pipe. Either a cylindrical pipe or a rectangular pipe. Right? So So that's again guided waves. And of course optical channels, you can have two kinds, the fiber optic or free space optic, right? You can have free space optical communication or you can have fiber optic communication. But really speaking, the fiber optic communication is the same thing as a waveguide. If you look for it, it's a cylindrical waveguide in which it so happens that the cylinder is very thin, right, and you are transmitting light energy through it, which is also electromagnetic energy. The actual propagation mechanisms are exactly the same, right? So they can be treated like that. And free space optical communication is like free space electromagnetic communication, except that typically, unlike in that situation, you typically like to focus the energy in a very narrow beam so that it goes from point A to point B effectively, right? It's very commonly used in free space probes that you send up, but it's also used for many terrestrial applications today. Right? So I think with this I'll conclude this talk on communication channels. Thank you very much.